In this chapter here, and we talked about really ionic nomenclature so far. We had type 1 and type 2. And they're both ionic, which means they both have a metal and a non-metal together. And as we talked about, it is always the metal when it's involved that's the most important in terms of how you go about naming things. So whenever you see that metal, that's really what you want to look at to help you determine what you should do. And for type 1, that metal has a fixed charge. And that's basically our group 1, 2, 3, our zinc, cadmium, and silver. And to name these guys, we use the whole name of the metal. And the non-metal, as we talked about, we kind of drop a little bit of the last part there, or a little bit more than the last part, and we put the IDE at the end of it. For type 2, it also is a metal and a non-metal. And once again, it's that metal that's important. And the difference is it has a variable positive charge. And that's usually your transition metals. And again, just to the right of the transition metals below the staircase, lead, tin, bismuth in that area, they could have a variable charge. So the additional thing that you have to do in a type 2 compound is when a type 2 metal is present is to figure out what the charge is on the metal. We could do that very easily because we will always know the charge on whatever it's bound to. So you can kind of work your way backwards to figure out the charge on the metal. And when we name it, it's pretty similar, except that we do add a Roman numeral. So we'll still use the whole name of the metal. We will add a Roman numeral. And again, the Roman numeral is the positive charge on the metal, not again how many you have. And our non-metal, again, still gets the IDE treatment at the end of it. So they're both basically named the same way, except with type 2, because it does have a variable charge, you do have to let people know sort of what the charge is on the metal in this particular case. You do not need to do that at all with type 1, and you should not use Roman numerals with type 1 metals because they can never be anything else. So you'll never find a sodium that's like +2. It's always going to be +1. So because it's always fixed, it's known to have that fixed charge. There's no need, and you should not put a Roman numeral with those guys. Any questions on any of that there that we talked about last time? Okay. So I think where we left off is around here, I think. This is sort of just a decision tree as to how to go about naming things. But again, it is that metal that really determines, and it's basically whether you need it or you don't need a Roman numeral is really the kind of decision to make. Also, the other important thing that we talked about where people make a lot of mistakes is, again, there's no prefixes ever used here in an ionic sort of naming, so never use a prefix. And doesn't matter how many of the metal you have, how many of the non-metal you have, we don't use a prefix with this type of naming. So always keep that in mind. Again, people always want to kind of use prefixes. The next type of compound we're going to talk about are type 3 binary compounds. And type 3 are a little bit different. This is going to go into really covalent bonding. And we're going to basically have two nonmetals here, which is what we talked about with bonding, that we're going to have sharing of electrons. So type 3 compounds definitely will be two nonmetals together. And speaking of prefixes, this is the proper place to use prefixes. So if you want to use prefixes, and again, if you want to use prefixes correctly, this is where you should use them. We will use prefixes like mono for 1. I think there's a table coming up. 2 for di. Tri is 3. Tetra is 4. Penta is 5. Hexa is 6. Hepta is 7. Octa is 8. Nona is like 9. And deca is like 10. So these prefixes are used here in type 3 compounds. They are probably the easiest ones to do. They should also be probably the fastest ones that you do. But they are also the ones that people really screw up the most because they try to do all kinds of weird things they don't need to do. So try not to do that as we go through it and talk about it. So again, this table we're going to see a little bit later on with the prefixes there. So type 3 only contain nonmetals, which means we do have that sharing of electrons. And pretty much the way that we name these guys is we use the prefix if necessary and the whole name of the first element that's in the formula. Then we use a prefix for the second name, and we give the second name kind of the normal treatment here that ends in the IDE sort of part, like normal. There are a couple of rules as we'll talk about, and as we'll see, the main rule is really no mono on the first name. But it is okay on the second. And the other major thing, as we'll see here, is very commonly what will happen is we'll have a prefix and it will go into the element name, and we'll end up with kind of two vowels that back up to each other. So we'll get kind of two vowels in a row. And the common ones that happens on is kind of like an A and an O will happen, or an O and an O. And typically speaking, this would be from the prefix. This would be from the element's first sort of letter. We typically will get rid of the prefix sort of vowel at the end. And just an example of both of these sort of rules here. If we take a look at CO, that is carbon, which is a nonmetal. That is oxygen, which is a nonmetal. So right away, that should tell you this is a type 3 compound, and we should be using prefixes. Again, we don't have to worry about charges or anything like that because they're sharing electrons, so there are no charges or anything. So we just basically need to count what's there. So we do have one carbon, which means the prefix would be mono. We also have one oxygen, which means the prefix would be mono. Again, here we will not use mono on the first name, so we'll use the whole name of carbon. We can use mono on the second name. And then the second guy gets the IDE treatment. Now, this is a case, as I was just talking about, where we will get backed up to each other here a couple of O's. And in this case, we will get rid of the O on the prefix. We don't call this carbon monoxide, right? We call this carbon monoxide, right? So we get rid of that O, and the proper second name then should be monoxide. So this is carbon monoxide. So whenever you have kind of an A and an O that backs up to each other, get rid of the A. An O and an O, get rid of the O. Two I's seem to be okay. So two I's coming out to each other is okay, but I've got main one is kind of the A and the O and the O and the O that backs up from the prefix to the first letter of the element name. Question on that. All right. Now, how do we go about naming these things? Come here. The first element is, again, always named first based on the formula. So we just kind of go in order. So that goes from when we're given the formula, we go with the first element to the second element, and also in the name as well. Obviously, based on the name that's given to you, you would go first guy is the first element, and the second guy would be the second. Prefixes, again, indicate the number of atoms that are present. And as we said there, mono is not used on the first element, but it is okay there on the second. So this is our prefix sort of table. And as we just talked about, here's another couple of examples. We have tetraoxide. Again, here we're going to get rid of the A off of that prefix, and it's going to be tetraoxide. And there's our mono that we're going to get rid of the O. There are still these guys that go by their common names, as we might have touched upon last time. Obviously, H2O is water, ammonia, which is NH3, and again, methane, which is CH4, is another one that you should do. So you should not call water dihydrogen monoxide. Yeah, you should just call it water, and you should not call ammonia nitrogen trihydride. Again, it should just be called ammonia. I think we also touched upon it last time, but just to reiterate, if we do have hydrogen in front of something like this, although this really is two nonmetals together, and it is sharing of electrons. It is named more like a type 1 compound, and we basically just call this hydrogen chloride. So again, hydrogen is sort of an exception. It is almost treated more like an ionic compound rather than the sort of covalent compound that's happening here. Even if we had two hydrogens here, this would be hydrogen sulfide. So if you do have, again, hydrogen sort of involved, even though technically it's two nonmetals, in most cases, it will not sort of follow type 3 rules. It can follow type 3 rules if it's maybe at the end of the formula and you got a nonmetal really before it rather than it coming first. For example, like say BH2 or something like that. This would be something like boron dihydride. So in this case, we would kind of use the type 3 rules rather than where we have kind of hydrogen in front of the nonmetal. We'll kind of go with just the type 1 type of rules. Any questions on that there? All right, so why don't you try these, and why don't you also write some names? Let's do nitrogen. Pentoxide. Let's do carbon tetrachloride. Let's just do dioxygen trioxide. I'll just not trioxide. I'll just try. Let's do I'll do trisulfide. I'll just make something up. Probably doesn't exist. We'll just go with it. All right, left-hand side there, proper names. Right-hand side, proper formulas here. Okay, let's take a look at these here and see how we're doing. So first thing, we want to identify what we're dealing with. I is a nonmetal, O is a nonmetal. So that automatically tells us it's type 3. We should use some prefixes. Remember, there's really nothing to balance in terms of charges. Pretty much just need to pick the right prefix for how many is there. So we have 2 for the first one. So that is a di for the prefix. We have 7 for the second, which is a hepta. And we will go di, the entire name there of the first element. And then we will go heptoxide here. We'll drop the A off of the prefix. And again, the second element there gets the IDE treatment. Any questions on that one there? Looking at the second one, there is 1 carbon, which is nonmetal. Oxygen is a nonmetal. So carbon 1 is mono. 2 is di. Once again, we don't use mono on the first name, so we will just use the whole name there, which would be carbon. And that would then be di, and this guy will get the IDE at the end. So that would be carbon dioxide. Lastly, here we got phosphorus is a nonmetal, Cl, which is a nonmetal. That is 1 of them, which is mono. That is 3, which is tri. Once again, no mono on the first name there. So that's going to be phosphorus. And we're going to have a trichloride happening here. Any questions on any of those names? So pretty straightforward. Just pick the right prefix and don't overthink it. Yeah. Now, the right-hand side, in my personal opinion, is probably the easiest of all of it, which is writing the formulas for these guys. And that's because when I look at this, I see prefixes, which tells me it's type 3. So I just need to write essentially what it says. So di is 2, nitrogen is N, penta is 5, oxide is oxygen. And now I am done with the formula. So, I mean, they should take you like a second to pretty much do these type 3 guys. Here, carbon, no prefix. But I do see tetra, which is a prefix, and carbon with no prefix means I just have 1. And tetra is 4, so a little Cl4 action there. And now we have the formula for that guy. And lastly, di, which is 2, tri, which is 3. So O2S3 in this case. Any questions on that there? So type 3 pretty much could go right through it pretty quickly. Again, you just don't want to do anything weird that people want to do. There is no mixture, as you can see here, no prefixes and Roman numerals or anything like that. So everybody has sort of their right spot to be used. This is only prefixes, nothing else should be done. Any questions on type 3? All right, so as we just saw there, type 1, type 2 ionic. So basically no Roman numerals, right? Type 2 needs Roman numerals, and type 3 needs prefixes, right? So again, each of these things has their own special thing of naming, basically. All right, little decision tree you can take a look at there. All right, the next thing we're going to talk about is polyatomic ions, and polyatomic ions are really groups of nonmetals together, and they actually are sharing electrons and covalently bonded, but because of how they are sharing electrons and who they're sharing electrons with, they actually end up having an overall sort of charge. And that means that if we take a look at an example like NH4NO3, we actually have, in this particular case, two different polyatomic ions. Let me break it up right about there. We have this guy right here, which is NH4 plus. That one nitrogen and 4 hydrogen stays together as a whole unit and has an overall charge of +1. This guy right here is 1 nitrogen and 3 oxygens with a -1 charge. Once again, that nitrogen, 3 oxygens stay together as a whole unit and has a -1 charge. This is essentially an ionic compound, which is why we have a +1 and -1, which is why when we look at the formula, we just need one of each of those polyatomic ions. We actually drew both of these when we did Lewis structures, right? So if you remember, this is NH4 plus. These guys are all sharing electrons with an overall charge of +1. And this is nitrate, our double bonded guy here. With an overall charge here of -1. So again, -1 and +1. This is why these guys will never break apart into the individual elements, because they're sharing electrons. So they're bonded together. That's also why they move around as a unit. So you want to keep that in mind as you're doing it. These guys have special names and also special formulas that go with it. So for example, this guy here is what is known as the ammonium ion, not to be confused with what we just saw, which is NH3 that has no charge, which is ammonia. So ammonia, NH3, no charge. Ammonium, NH4 with a +1 charge. So they are different, those things. NO3 minus is what is known as the nitrate ion. The good news about polyatomic ions is this: you just use the name. It doesn't matter how many of them you have. You pretty much just use the actual name of the polyatomic ion when you go to name it. So that is what we would name this guy. First guy is ammonium. And second guy is nitrate. So this would be ammonium nitrate. We just use pretty much the whole name of the polyatomic ion. And again, no difference if there's one of them or 30 of them. We just use basically the whole name of it in the particular formula. Question on that there. Now, for the most part, most polyatomic ions are negatively charged. There's a few positive ones like this one. Hydronium ion is also positive, but the vast majority of polyatomic ions are actually negatively charged. So what usually happens when we have a polyatomic ion is usually will be hooked up with a metal. So a lot of times you will see a metal and a polyatomic ion together, as the polyatomic ion being negative and the metal being positive. So what happens in a lot of cases when we have a polyatomic ion and definitely a metal, and as we talked about with type 1 and type 2, whenever that metal is involved, it is really the important thing in terms of how you name it. So a lot of times we will fall back to our type 1, our type 2 naming, when we're dealing with a polyatomic ion, because again, that metal sort of determines how you name it. So for example, here, if we were to look at, let's say here we had FeNO3 2, for example. Here we would look at it and go, that's a metal, and that is a polyatomic ion. Once again, because the metal's involved here, it is the one that's most important, and that is iron, which is a transition metal, which should tell us it is a type 2 situation that's happening here. So we do need a Roman numeral when we go to name this. We would do the same approach. We know we have one iron, and we have nitrate, which has a -1 charge, and there are two of them, which means overall -1 is -2. So just like before, to balance it out here, our iron in this particular case would be +2 to balance it out. And we do have to include that in the name, just like we would with a type 2 metal. And this would be iron Roman numeral 2, once again for the charge on the metal. And again, even though there are two of the polyatomic ions, it has no effect on the name, so we would just call it nitrate at the end, and this would be nitrate. Any questions on that there? We also see in the formula that I actually put parentheses around the polyatomic ion, and you should always do that when you have more than one polyatomic ion and you're writing a formula for it. You do need to put parentheses and how many there are on the bottom right. That is because if I just wrote it like this, that would imply I have what? About 32 oxygens, which is clearly not the case here. If we look over here, I only got about 6 oxygens that's actually happening. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom as a subscript as to how many you have. Again, will not have an effect on the name, but you do need to do that when you write the formula. If you just have one polyatomic ion in a formula, you don't need to put the parentheses. So sometimes people parentheses up everything. So you don't need to put the parentheses if there's just one. Also, if I had something like this, this would be NaNO3. Na is sodium, which is a metal. NO3, as we've been seeing, is nitrate. And again, it is the metal here that determines. So sodium's a type 1 metal, which has a fixed charge, which means we do not need a Roman numeral, and this would be known as sodium nitrate. It is made up of a sodium ion and a nitrate ion. -1 + 1 = 0. So 99 times out of 100, probably you will find a polyatomic ion pretty much hooked up with a metal. You could fall back on pretty much the type 1, type 2 rules and just use the whole name for the polyatomic ion. Any questions on that there? So here's a list. Here's another list of some polyatomic ions. They're up on Canvas as well separately, I think, as PDFs in the exam review if you want a kind of a bigger version of it. But these are the polyatomic ions, and it's a good way. You do have to unfortunately memorize these. They want you to know these. So you need to know the names. You need to know the charges that go with it so you can balance out everything. But there is sort of a way that you can kind of look at these and sort of maybe figure out and learn them. So there are patterns when we look at polyatomic ions. So for example, if we had our NO3- that we just saw there, which is nitrate, AT, we have NO2-, that is nitrite. We have something like SO4 2-, that is sulfate, and SO3 2- is sulfite. So you can kind of group these things up as like groups of 2, and there's also groups of 4 as well. But with a group of 2, with the most oxygen will end in 8, and the one with the least number of oxygen will end in ite, and that's what we see here. They all have the same charge in this case, right? NO3-, NO2-. They both have exactly the same charge. The only difference is the number of oxygens. The one with more oxygens in this group ends in 8. The one with least oxygens ends in 8. Here, SO4 2 minus and SO3 2 minus. They both have the same charge. The one with more oxygens ends in 8, and the one with least oxygens ends in 8. So usually the one that ends in 8, more oxygens, and the one that ends in 8, less oxygens. Now, there are ways that you could help yourself sort of remember these. So sometimes people will, for example, remember all the ites and their formulas and just know that if I need an 8, just add an oxygen, everything else is the same. Or you could do the opposite, remember the 8s and know if you need an ite, just drop off an oxygen from it. So that's a good way to sort of remember it and figure it out, is just maybe learn one of those guys, the 8s or the ites, and know that to adjust it, either add an oxygen or drop off an oxygen from its name. So what do I mean by that? For example, this guy is phosphate. And if I wanted phosphite, it should have one less oxygen. Everything else would be the same. So it would just drop off basically one oxygen and will be the phosphite. So if I had this guy, which is carbonate, and I wanted carbonite, how many oxygens should it have? 2, it'd be CO2 2 minus. So again, that is a way you could kind of adjust it if you just maybe learn one of them and know go up or down based off of that. Any questions on that there? There's also groups of 4 that are related to each other, and the most common group of 4, maybe I'll do it over here ish maybe, is really yeah, another table in case you missed it. I'll do this one here. This group of 4 is related to each other: ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. So all these are related to each other. They're all basically have a -1 charge. The only difference is the number of oxygens in each of them. So all these guys, all -1s. So in a group of 4, what you could do is the same thing. You kind of break it up by 2s. So if we go to the right-hand side, those are guys that have the least number of oxygens in that group of 4, and they should end in ite, right? Because the least number of oxygens should end in ite. So this would be chlorite. This guy here would be chlorite. You clearly cannot have the same name for 2 different things. So when you have a group of 4, the one that has the least number of oxygens in that group of 4, in addition to ending in ite, will start with hypo. So the guy at the end was known as hypochlorite. We could do the same thing for the guys on the left. They have the largest number of oxygens in this group of 4, which means they all should end in 8. So this would be chlorate. And this guy would be chlorate. Again, we can't have 2 names for the same thing, or same name for 2 different things. So in this case, in a group of 4 that has the most oxygens in a kind of a run of 4, we'll actually start with per in front of it. So this is what is known as perchlorate. So there are groups of 4 that are related to each other. You can kind of break them up the same way. Ite and 8 should be the endings. And again, the additional for those guys at the ends, per for the guy with the most oxygens, and hypo for the least. The guy right there is Cl, which is a halogen. You could replace really that halogen with any halogen. It's named the same way. If you had to take a guess, what would BrO3 minus be? ClO3 minus is chlorate. So BrO3 minus should be bromate. Yeah. BrO2 minus should be bromite. Yeah. So again, you could swap it out for any of those halogens. IO3 minus would be iodate. Yeah. So again, this is how you could kind of pretty straightforwardly, hopefully, figure out some of these polyatomic ions. So there are groups of 2s, groups of 4, they're related to each other. Any questions on that there? A couple other things, if we look at the table that we will see. Erase some of my scribbling here. There are certain ones where we add, for example, hydrogen in front of it or H plus in front of it. So we looked at our carbonate, which is CO3 2 minus. That is carbonate. And if I put an H plus in front of it, that gives me HCO3 minus. The charge changes because it's +1 -2 and ends up as a -1 charge. I essentially put hydrogen in front of it. So this is what is known as hydrogen carbonate. And hydrogen carbonate, or hydrogen, is also still historically used and very commonly used as bi instead of hydrogen. And this is what is known as bicarbonate. Also happens with sulfate and phosphate. That's hydrogen phosphate. We have bisulfate as well that happens with. So you could have something like, this is SO4 2 minus, which is sulfate. Putting that H plus in front of it gives you HS, too many H's, HSO4 minus, which is bisulfate or hydrogen sulfate. So that's another very common thing that you'll see on a polyatomic ion table. For example, you could also have dihydrogen phosphate, which has 2 hydrogens here as well. So you'll have some of these other things that can happen on our polyatomic ion table. Although a vast majority of them do end in either ite or ate, there are some polyatomic ions that do end in IDE as well. So hydroxide, OH minus, ends in IDE. Cyanide as well ends in IDE. Azide as well ends in IDE. But a vast majority of them will be, again, probably ATE or ITE in terms of it. Any questions on that there? All right, so let's try a few here just to make sure. All right, I'll leave this table up here. So we'll do, what is the name of the following here? Let's do CuOH2. Let's do NiSO4. Let's do Na2CO3. And then why don't you also write the name for iron 3 cyanide. Why don't you do sodium chlorate. And why don't you do ammonium sulfide. All right, so names for those guys that are formulas and formulas for the guys that have the names there. And we want to kind of identify what we got going on. We'll start up here. That is sodium, which is a metal. That is CO3, which is carbonate. So that is basically our sodium ion and our carbonate ion here. And again, because the metal's involved, that's really most important. And that metal is a type 1 metal, which means we do not need a Roman numeral. So there's really nothing to figure out at this point to name it. We'll use the whole name of the metal, which would be sodium. And we would use the whole name of the polyatomic ion, which would be carbonate. Any questions on that? Just like with type 1, it doesn't matter. There's 2 sodiums, has no effect on the naming. Any questions on that one there? Taking a look at the one there here in the middle, that is copper, which is a metal. That is hydroxide, which is a nonmetal. In this case, that copper is a type 2 metal, which means we do need to figure out the charge on it. We do know that hydroxide from the table here is OH minus, and there are 2 of them, which gives us a -2 overall sort of charge. We have only 1 copper in this case, so to balance it out, it needs to be +2 in this case, and that means it does need a Roman numeral here, and I'll just write it over here. That would be copper, Roman numeral 2, again for the charge that's on the copper, and even though there are 2 of the hydroxides, has no effect on the name, it would be hydroxide in this case. Any questions on that one there? Looking at the last one, that is Ni, which is nickel. Also a transition metal, which tells us it's a type 2 metal. SO4 is sulfate. So here again, we need to figure out the charge on the nickel. Our sulfate from our table is SO4 2-, which means it has a -2 charge. That means to balance it out in this case, our nickel has to carry a +2 charge, and we would again here need a Roman numeral. And for our Roman numeral there, it would be 2. And I'll just write it up here. This would be nickel, Roman numeral 2, and our sulfate. Any questions on any of those names there? Now going backwards here from the formula to the name, we're just going to basically put it together. I have iron 3, which I know is iron with a +3 charge because of that. Cyanide is right there, which is Cn-. So in this case, as an ionic compound, we want to get to 0. We basically need not one of these guys, but we do need 3 of those guys to balance out the charge. And that would get us our proper formula here of Fe. We do need to put parentheses because there's more than one of them, of these polyatomic ions, CnNa3 on the bottom there. Any questions on that one there? Coming at the next one, which is sodium chlorate, it looks like I wrote. And sodium is group 1, which means it has a +1 charge. Chlorate's one of our group of 4 that are related to each other, which is actually ClO3-. We are ultimately putting a +1 and -1 together, which means we just need 1 of each. And that would give us, I'll put the formula over here, NaClO3. Once again here, because we only have 1 of the polyatomic ions, there really is no need for parentheses or anything like that in the formula. Any questions on those too? Yeah, so these are really polyatomic ions when they hook up with metals or just in general. They're really ionic compounds. So just like our ionic compounds we talked about with type 1, type 2, whenever we put that positive negative guy together, we want 0 overall charge. So there should be no charge in the formula when they come together, just like type 1, type 2, but they are made up of 2, individual sort of ions and stuff like that. So other questions? Okay, lastly here we have ammonium sulfide. Ammonium is our few positive guy right there, NH4+, and sulfide is actually from the periodic table, group 6, which is -2 there. So we basically have NH4+ and -2. In this case, to balance out the charge, we will need 1 more of those positive guys. And since that is actually a polyatomic ion, we again need the parentheses. So that's going to be NH4, 2, and S in this case there. Any questions on any of those polyatomic ions? All right, so the school would like you to know these, yes? So probably learn this table. You'll have pretty much all of the ones you probably will need, I assume, as you go through life in chemistry. Any questions on that there? Yeah. And again, obviously, they will not be provided for you. Yes. Okay. All right. There's a few more tables in case you missed it. All right. So we talked about these patterns, but again, just to reiterate, to look at these slides here. Again, in a group of 4, we're going to put per on the one that has the most oxygens. Going to start it with that, end with 8, and the one with the least oxygens, hypo as well. So again, you could adjust up or down just by learning one of them. So again, if that's sulfate, what happens if I wanted persulfate? How many oxygens should it have? Persulfate, so 8 means more oxygens, right? And per means that it should have actually one more than this guy, right? So that would be like SO5 2 minus, right? If I wanted sulfite, ITE should have one less. If I wanted hyposulfite, it should be SO2 2 minus. Yeah. So again, you could adjust up or down in that sort of group of 4. If you can go sort of the basic one of those and kind of adjust. Again, everything else stays the same with these guys. The charges stay the same. It's just really the number of oxygens that change as you kind of go up or down. Any questions on that there? All right. And again, as we saw there, we can swap out a halogen and it will be named the same way. And also when we add hydrogen, remember that when we do add the hydrogen, it's really the hydrogen ion. So that plus is important because it does adjust the charge. You know, as we said, we went from carbonate to hydrogen carbonate. It is not just the H that we're adding, but that plus 1 and -2 gives us a -1 left over. So you got to adjust the charge as well when you add the H plus to it. All right. There you go. I'll just scroll through these since we kind of really covered all this as we went through it there. All right, the next thing that we're going to talk about is naming acids. And acids are substances that have the ability to produce H plus ions in solution. H plus ions are sometimes referred to as protons. And that is because, as we know, hydrogen has 1 proton, right? 1 electron and no neutrons. So when something becomes positively charged, it lost an electron, which means hydrogen is just left with a proton at this point. So that's why it's sometimes very commonly referred to as a proton in acid-base chemistry. Also, as we'll see when we get to the acid-base chapter, H plus and another polyatomic ion, H3O plus, which is known as the hydronium ion. Hydronium ion. Are basically the same. So they're used sort of interchangeable in acids. So especially when you're doing acid-base type of chemistry, you'll see H plus, H3O plus sort of used interchangeable. They basically both mean the acid part of the solution. But for our acids, H plus is really important. All acids can be thought of as really a ion and an ionic compound. And the cation for all acids, the positive ion for all acids, is H plus. So that is like basically your positive guy for all acids. Acids are really, again, as I said, they're something that can produce H plus in solution. And it basically means that when you have a solution, the amount of H plus you got floating around will determine, if it's acidic, basic, or neutral, really. And because of that, acids also, when you write the formulas, should typically have aqueous next to it. And aqueous means water environment, that's a solution. And so typically when you do write the formulas for your acid, you do want to put that little aqueous symbol next to it. Because, for example, if you had something like HCl that's aqueous, that is hydrochloric acid. You have like HCl that's like in the gas phase, that is called hydrogen chloride. So the aqueous part is really important for an acid. Basically, you could take the hydrogen chloride gas, bubble it through water, and now you have aqueous hydrochloric acid basically in that solution. So it's really important to make sure you always include that aqueous on your formulas for things that are acids. So let's talk about pretty much the rules for acids and naming them. And it really all comes down to pretty much, is there oxygen or is there not oxygen basically involved? And if there is oxygen versus no oxygen, we do name it differently. I'm just going to look for a clear page to do this, I think. I'm just going to summarize it here, I think. So when we go about naming acids, it's all about that oxygen. So if the answer is no, there is no oxygen involved, the acid name starts with hydro, something ic acid. The middle part that's missing is the negative ion that's attached to the hydrogen. So again, hydrogen is always going to be the positive guy. The negative guy is what the missing part of it is. So again, here, if we had our HCl, as we just saw, there is no oxygen here. This is basically H plus and Cl minus. And this would be, again, our hydrochloric acid, again, based off of our negative guy here. HBr then should be hydro what? Bromic acid. Again, Br minus, H plus, yeah. How about H2S? That's an acid here. That should be what? Hydro sulfur, right? So hydrosulfuric acid, yeah. There are two hydrogens here because sulfur is a -2, and we would need 1 and 2 of those hydrogens to balance out the charge. So hydro, which people want to use on every acid name, is only for acids that do not have oxygen involved. So if there's no oxygen involved, it should start with hydros and end with ic, and the middle part should be kind of the negative guy's name, sort of filling in this space there in the middle. Any questions on that one? HI would be what then? HI should be hydroiodic acid, yeah? So this would be hydroiodic acid. HCN would be, so is CN is cyanide, right? So this would be hydrocyanic acid, yeah? So that is what this would be, hydrocyanic acid. All right, so no oxygen, start with hydro, end with ic, kind of fill in the middle part with the negative guy. Now, if it does contain oxygen, it's a little bit different, and it will contain probably one of those polyatomic ions that we just saw on that list. So if you do have an acid that does have oxygen in it, and again here, maybe I'll clear out some of this side of this thing, and we'll borrow it here. Okay, so if we have an acid and the answer is yes, there is oxygen, it will contain your polyatomic ion in it. And as we saw, they pretty much end in ate or ite, right? These are also sometimes referred to as oxyacids because they contain oxygen. So that's why they're referred to, obviously, as oxyacids. So starting with if it does contain oxygen and your polyatomic ion ends in ate, your acid name will be something ic acid. So if we take HNO3, NO3 is nitrate, which means this would become nitric acid. H2SO4. SO4 is sulfate, which means this should be called, what do you think it should be called? Sulfuric acid. Once again, there are two hydrogens here to balance out the charge on the sulfate, which is -2. So again, the top guy there, there's only one hydrogen. because this guy is nitrate that has a -1 charge. So they all balance each other out. So you could think really as acids, it's like ionic compounds. You want to balance out the positive charge from the hydrogen with the negative charge to equal 0. Even though in reality, these are all basically sharing electrons, they're all sort of covalently bonded. In terms of naming, we kind of think again of it as more ionic, because when it goes into solution, it's able to release that hydrogen as an ion and create an ion as a result of that. This guy right here, H3PO4, that is phosphate, which means this should be called phosphoric acid. Yeah. Let me have our IC. Any question on those there? Now, if it, I'm just gonna put a box this way, maybe. If it does contain oxygen, and your polyatomic ion ends in ite, your acid will be something OUS acid. So HNO2, for example. NO2 is NO2 minus, which is nitrite. And that means that this acid should then be called nitrous acid. Yeah. Nitrous acid. H2SO3. SO3 is SO3 2 minus, which is sulfite, which means this should then become sulfurous acid. So this would be sulfurous acid. How about HClO? What would that one be called? And what would HClO4 be called? Here we want to see it has oxygen, so that's a polyatomic ion. That is ClO minus, which is hypochlorite. And you do keep the hypo in the name here, so this would be hypochlorous acid, as that's hypochlorite. This right here is ClO4 minus, which is perchlorate, and you would keep the per in it, and this is perchloric acid. So again, even on those polyatomic ions where they got the per or the hypo in it, you do keep that with the acid name, and again, just end it sort of differently. Any questions on that there? There is absolutely no hydro here with oxygen involved. So if there's oxygen, you should not use hydro. Hydro is specifically for guys that do not have oxygen. Any questions on how to name acids? All right, so that again is what we just went over there. So ic or us, if it does contain oxygen and a polyatomic ion, hydro if there is no oxygen involved, and ending with ic. There we go. So there's a table from your book, and again, there's all these guys do not have oxygen, so you can see they all start with hydro. They all end with ic, and again, the middle part is based on the negative ion that is present. So this would be H plus and F minus, H plus and Cl minus, and obviously, as you can see there, hydrosulfuric acid and hydrous ionic acid we did as well. These all have oxygen, which are oxyacids. They all contain polyatomic ions, which are the ones underlined here. That right there is acetate, and that is how we get acetic acid, which is basically like vinegar, as the name for that particular one as well. All right, so we kind of solved both of those. So HF has no oxygen, so that should be the hydrofluoric acid. And this one does have, again, our oxygen, and that was, as we saw earlier, nitrate, which means it should then become our nitric acid. Any questions on acids or how to name it? By the way, if you have the name, for example, if you had phosphoric acid and you're not really sure like how to go backwards, right? So you could use the name to your advantage. The first thing that you should know is an acid, which means the positive guy should be H plus. So that's automatically, you should know that. What I look here when I look at this part of the name is there is no hydro, right? Which means that this guy does contain oxygen. And because it does contain oxygen, I know that it's a polyatomic ion. And I know that my polyatomic ion will probably end in either 8 or ite. And I know that when I do it for the acid, this one particularly ended in ic, which means that the polyatomic ion should end in 8. Yeah, if you kind of go backwards. So frankly, if you just cross out the ic and put an 8, phosphorate, yeah, so now you know what polyatomic ion it is. And then you would now proceed basically just to put together like normal. So in this case, we would need our 3 hydrogens to give us our H3PO4. So if I had something like, we'll do our hydroiodic acid, we'll do our, let's do our carbonic acid. And let's do our let's do chlorous acid. All right, so write the formula for each of those 3 there as to what it should be. Okay, so let's take a look. So once again, these are all acids. And we know that for sure that the positive guy is going to be H plus in this case. When I look at this one, I see hydro, which tells me there is no oxygen involved. So I don't have to worry about a polyatomic ion and iodic there. It looks like iodine. And that is group 7. So we're just going to put that together to get us our H. And again, we do want to put the aqueous symbol next to it to indicate that it is an acid. When I look at carbonic acid, there is no hydro, which tells me it does contain oxygen. And that means that, again, the H plus is going to be the positive guy. This ends in ic, which means if I cross it out, my polyatomic ion ends in 8, and that's like carbonate. And I know hopefully at some point that that is CO3 2 minus. So again, we want to put it together to balance it out. So we're going to need 1 more hydrogen, and that will give us H2CO3. Any questions on that there? So again, you can kind of use the name to work backwards. Once again, here on the bottom, I see no hydro, which tells me that, again, it's a polyatomic ion, and it contains oxygen. I see chlorous, so OUS means that the polyatomic ion ends in ite, so that is chlorite. So I know that that is ClO2 minus. So now all I have to do is put it together properly, and that would be HClO2 and aqueous. Any questions on going from the acid name back to a formula? So that's a really good way to do it. Cross out the back part, put ite or 8 if it contains oxygen, and that will definitely tell you pretty much the name of the polyatomic ion, and you could get the correct formula. Any questions on that there? Okay, we will lay it up. That is